Chapter 4, Exponential and Logarithmic Functions, Section 4.2, Logarithmic Functions. So in the previous section we introduced exponential functions, and now we're going to talk about the cousins of exponential functions, which are logarithmic functions. We'll introduce logarithms in particular by way of an example. And this is based on compound interest, which we studied again in section 4.1. Suppose we take suppose we invest $1,000 at 8% interest compounded annually and wish to know how long it will take to double our investment. Using the formula A equals P times the quantity 1 plus R raised to the T power. This is the formula for annual compounding of interest from section 4.1. We have P equal to 1,000, that's our initial investment. R equals 0.08, that's our interest rate as a decimal, 8%. And we want to find T such that our future value A is $2,000 because we're trying to determine how long it will take to double our investment of $1,000. So this requires us to solve the equation. So substitute 2,000 for A, 1,000 for P, 0.08 for R. The 1 plus R therefore becomes 1.08. So we have the equation 2,000 equals 1,000 times 1.08 to the T power. If we divide both sides of that equation by 1,000, then on the left-hand side we would just have a 2. And what I've done is just switch the equation around with the 1.08 to the T on the left and the 2 on the right. So we have the equation 1.08 to the T power equals 2. So now the problem becomes one of finding an exponent T such that if we raise 1.08 to that exponent, we will obtain 2. So the difference here in terms of what we were talking about previously and what we're talking about now is that we're solving for an unknown in the exponent. This is called an exponential equation. Well, it turns out that the exponent we want can be expressed as what we call a logarithmic expression. T equals log base 1.08 of 2. This represents the exponent 1.08 should be raised to give us the number 2. So the exact value of this exponent is written as this logarithmic expression, which, if you're not familiar with logarithms, and even if you are familiar with them, is kind of an unusual looking notation. And it does not look like an exponent, but that's actually what it is. So it's read logarithm base 1.08 of 2, or just log base 1.08 of 2. Now, if we know how to approximate this logarithmic expression on a calculator, and you'll eventually learn how to do that, we would see that it's very close to being equal to 9. So we conclude that it will take approximately 9 years to double our investment under annual compounding. You could check that by taking 1.08 to the 9th power and verifying that that's very close to being equal to 2. So as I said, we'll learn about computing or approximating such logarithmic expressions later. But for now, note that the solution requires finding an unknown exponent, and that this exponent is referred to as a logarithm. So perhaps the most important thing to remember about logarithms is that they represent exponents. Now here's the formal definition. Let A be a positive real number with A not equal to 1. The exponent to which A must be raised to produce a positive real number x is written log base A of x. So log base A of x is the exponent to which A must be raised to produce x. This is called the logarithm base A of x. So we have this equivalence. This is very important to remember this equivalence. Log base a of x equal to y is equivalent to a to the y equals x. If we take the logarithmic expression, starting with the base of a, and make a little circle like this, then we can convert it to this form, a to the y equals x. So I'm going to show you that in some of the examples that we'll be following. For example, if we want to know the exponent to which 2 must be raised to produce the number 8. Okay, we know that exponent would be 3, 2 to the third equals 8. We want to solve the equation 2 to the y equals 8 for y. The exponent is called the logarithm base 2 of 8. It's logarithm base 2 because 2 is the base of this exponential expression. The logarithm can be written log base 2 of 8. Now, be careful with this notation here. Log base 2 of 8, we're not talking about 2 to the 8th power. It looks a lot like 2 to the 8th power, but that is not the interpretation. It's actually, we're asking what is the exponent 2 must be raised to give us 8. Since we know that that exponent is 3, it follows that log base 2 of 8 equals 3, and this is equivalent to writing 2 to the third equals 8. That's the equivalent exponential form. So one of the things we have to kind of get used to is this, what seems to be rather unusual notation for exponents, this logarithmic notation. And this is one of the problems that students run into with logarithms, is just understanding what they're actually working with, because the notation sometimes gets in the way a little bit. So we refer to the equation a to the y equals x as exponential form, and the equation log base a of x equals y as logarithmic form. We can convert easily from the logarithmic to the exponential form by remembering this little method I showed you a moment ago. A to the y equals x. I usually say think in a circle. Start with a base, a to the y equals x. I'll demonstrate this in the following examples. But these two forms, exponential and logarithmic, are two ways of stating the same thing. Sometimes the logarithmic form is more convenient. Sometimes the exponential form is more convenient. Example 1 says, write the logarithmic equation in exponential form. So our first example would be read, log base 3 of 81 equals 4. What we do is we start with the base, we go to the 4, and then we go to the 81. So the exponential form of this would be, start with the 3 to the 4th power, then set it equal to 81. Second example, log base 10 of 1/1000th equals -3. Start with the 10, raise it to this power, set it equal to that. 10 to the -3 equals 1/1000. And we know, by the way, 10 to the -3 is 1 over 10 to the +3. 10 to the +3 is 1000. So this is, when we write it in exponential form, we should obtain an equation. If all of the values are known, we should obtain an equation that is fairly obviously true, at least if we're dealing with kind of a simple situation like we're showing in example 1. Now, we can also convert from exponential form to logarithmic form. I don't have a little trick to show you for this, but I can kind of give you a sense of how you would deal with this. Write the exponential equation in logarithmic form. 5 to the 0 equals 1. Okay, well, what I would say is, first of all, write the word log. That's the easy part. What is the base of the logarithm? Well, the base of the logarithm is identical to the base of the exponential expression. So that would be a base 5 logarithm. Write it as a little 5 as a subscript. Okay, the next thing I'm going to do is say, what is the value of the logarithm? What's it equal to? Well, the value of a logarithm is whatever the exponent is. A logarithm is an exponent. So the value of this logarithm would be 0, because that's what our exponent is. And then what we put in here is a 1. And again, please understand, we're not writing 5 to the first. We're writing log base 5 of 1. In fact, you can put parentheses there. Basically, log base 5 is like a function. It's like f of 1, really. Log base 5 of 1 equals 0 is the equivalent logarithmic form. Second example, similar idea, no numbers involved here. C to the r equals b. Well, first of all, we write log. Okay, what's the base of our logarithm? The base of our logarithm is the same as the base of the exponential expression. So it's a base c logarithm. What's the logarithm equal to? The logarithm is equal to whatever's in the exponent. So the logarithm is equal to r. Okay, that means the only thing left is to put b right here. Log base c of b is equal to r. So, and then, if we check by using the little circle trick I showed you, c to the r equals b, it takes us right back to that exponential form that we started from. So that is how we can convert from logarithmic to exponential form, or vice versa. Moving to the second page of the notes and to example 3, we want to find the value of a couple of logarithmic expressions. We're going to use this method of converting to exponential form. Find the value of the logarithm. The first example is log base 5 of 25. What we're going to do is give this a name. I'm going to call it y. And really, it's better to use y than x here. So I encourage you, if you're finding the value of a logarithm by converting to exponential form, use the variable y. Hopefully you'll see why that would be a good idea as we go further into the notes. The exponential form of this, by converting to exponential form, would be 5 to the y equals 25. So y would be the exponent 5 should be raised to give us 25, and then it should be pretty obvious that y would have to equal 2. So that means 2 is the value of our logarithm. Log base 5 of 25 is equal to 2. Because 2 is the exponent, 5 should be raised to give us 25. Second example can be done in a very similar way. Log base 2 of 1/2, what is its value? Well, call that y. Write it in exponential form. Start with the base of 2, raise it to the y power, set that equal to 1/2. Well, what is 1/2? 1/2 is 2 to the negative 1 power. So it would have to be the case that our exponent should be negative 1. The value of the exponent is the value of the logarithm. So log base 2 of 1/2 is equal to negative 1. Because negative 1 is the exponent, 2 should be raised to give us 1/2. We'll continue with the notes in the next video.